Welcome. In this video, we are going to cover everything you need to know to pass the Certified Kubernetes Administrator exam, the CKA. We are talking architecture, pods, deployments, networking, storage, RBAC, scheduling, cluster maintenance, and troubleshooting. This is your complete study guide. Let's get into it. Next, let's start with the basics. What exactly is the CKA? The Certified Kubernetes Administrator is a performance-based exam run by the Linux Foundation and the Cloud Native Computing Foundation, the CNCF. And when I say performance-based, I mean this is not a multiple-choice quiz. You sit in front of a live Linux terminal, and you have to solve real Kubernetes problems using kubectl and other CLI tools. The exam covers 5 main domains. Cluster architecture, meaning you need to understand and be able to deploy all the components that make up a Kubernetes cluster. Workloads and scheduling pods, deployments, resource limits, scheduling rules, services and networking, how to expose applications and control traffic, storage, persistent volumes and claims, and finally, troubleshooting, diagnosing broken pods, nodes, and services. Here are the key exam details you need to know. You get 2 hours. The format is a live CLI environment. It is open book, meaning you can use the official Kubernetes documentation. The passing score is 66%. Your certification is valid for 3 years. And the exam environment runs Ubuntu 20.04 with kubectl, Vim, and TMUX available. And look at the pie chart on the right. Notice that troubleshooting alone is worth 30% of the exam. That is the single biggest domain. We will come back to that. Before we touch a single kubectl command, we need to understand how Kubernetes is actually structured. This diagram shows you the full picture. A Kubernetes cluster has 2 types of machines, the control plane and the worker nodes. The control plane is the brain of the cluster. It has 4 main components. The kubeAPI server is the front door. Every single interaction with the cluster goes through it. The etcd is the cluster's database, a distributed key value store that holds the entire state of your cluster. The kube scheduler watches for pods that haven't been assigned to a node yet and decides where to place them. And the kube controller manager runs background loops that continuously reconcile the desired state of your cluster with the actual state. On the worker nodes, each node runs 3 things. The kubelet is the node agent. It receives instructions from the API server and tells the container runtime to start or stop pods. The container runtime, most commonly container today, actually manages the containers. And kubeproxy handles the networking rules on the node, using IP tables or IPVS to route traffic to the right pods. On the work container is simple. You send a command via kubectl. It hits the API server. The API server writes intent to etcd and signals the scheduler and controllers. The scheduler picks a node, and the kubelet on that node instructs the container runtime to start your pods. Next, let's go one level deeper on the control plane components because the CKA will test you on knowing exactly what each one does. Click kubeAPI server. This is the REST gateway to your entire cluster. Every kubectl command you run is ultimately an HTTP request to the API server. It validates your requests, checks authorization via RBAC, and then reads or writes the desired state to etcd. You can inspect it with kubectl get pod-n kubesystem kubeans-api server less than node greater than. Click etcd. This is where all cluster state lives. Nodes, pods, secrets, config maps, everything. It is a distributed consensus system using the Raft algorithm. For the CKA exam, the critical skill here is knowing how to back it up and restore it. The command shown uses etcdctl with etcdctl _API equals 3, and you must supply all 3 TLS certificate flags. We have a dedicated slide on this later. Click kube scheduler. When you create a pod, it starts in a pending state with no node assigned. The scheduler watches for these unscheduled pods and assigns them to the best fit node based on resource requests, taints and tolerations, affinity rules, and available capacity. Click kube controller manager. This runs dozens of controllers as a single process. The replica set controller ensures the right number of pods are running. The node controller monitors node health and marks them not ready when they go down. The endpoint controller keeps service endpoint lists up to date. Click kubelet. This runs as a systemd service on every node, not as a pod. If the kubelet dies, the node goes not ready. When troubleshooting node issues, systemctl status kubelet and journal ctlu kubelet are your first stops. Now let's talk about pods. The pod is the smallest deployable unit in Kubernetes. You don't deploy containers directly, you deploy pods, and each pod wraps 1 or more containers. All containers in a pod share 3 things. The same network namespace, meaning they share an IP address and can communicate over localhost, the same storage volumes, and the same lifecycle. If the pod dies, all containers in it die together. Look at the YAML on the left. This is a minimal pod manifest. You have API version, kind, and metadata at the top. Those are on every Kubernetes resource. In the specs section, you define your containers. Each container has a name, an image, and optionally resource requests and limits, environment variables, and probes. Click on the right. Here are the essential kubectl commands for working with pods. Kubectl apply, netix fpod.yaml, to create or update. Kubectl get pods, oy to see which node each pod is on. Kubectl describe pod, to get events and detailed status. Kubectl logs to read std out. Kubectl exec, it to get a shell inside the container. Click and at the bottom, the 5 pod phases. When a pod is first created, it enters pending, while the scheduler assigns it, and the image is pulled. Then running. Succeeded means all containers exited cleanly with code 0. Failed means at least one exited non-zero. And unknown means the node stopped reporting, usually a network problem. Next. In practice, you almost never create pods directly. You create deployments. Look at the diagram. A deployment defines your desired state. I want 3 replicas of this application. The deployment creates a replica set, which is responsible for ensuring exactly 3 pods exist at all times. If a pod crashes, the replica set controller notices and creates a replacement automatically. Beat the deployment YAML is shown on the left. Key fields to know. Replica sets the count. The selector.match labels tells the deployment which pods it owns. The strategy section controls how updates are rolled out. Rolling update with max surge, 1 and max unavailable. 0 means Kubernetes will spin up 1 new pod before terminating an old one, achieving 0 downtime deployments. Click. Here are the critical deployment operations for the exam. Kubectl scale, to change replica count. Kubectl set image, to trigger a rolling update to a new image version. Kubectl rollout status, to watch the progress. Kubectl rollout undo, to instantly roll back to the previous version. This is a lifesaver when a bad image gets deployed. And Kubectl rollout history to see all past revisions, and roll back to a specific one with to revision. Beat internalize these commands. The CKA will absolutely ask you to perform a rolling update and then roll it back. Pods are ephemeral. They can be created and destroyed at any time. Their IP addresses change. So how do clients reliably reach your application? That's what services are for. A service is a stable virtual IP and DNS name that sits in front of a set of pods. It uses a label selector to dynamically find the right pods. When pods come and go, the service's endpoint list updates automatically. Look at the diagram. A client hits the service's cluster IP. The service load balances the request across all matching pods using kubeproxy's IP tables rules. There are 4 service types. Cluster IP is the default. It creates an internal-only virtual IP, accessible only within the cluster. Node port exposes the service on a static port, between 30,000 and 32,767, on every node's IP address, making it reachable from outside. Load balancer provisions a cloud load balancer automatically, used in AWS, GCP, Azure. External name is a DNS alias to an external hostname. Click the YAML on the right, shows both a cluster IP and a node port service. The key field is selector. It must match the labels on your pods exactly. On the bottom, the imperative shortcut kubectl expose is the fastest way to create a service in the exam. Always test connectivity with a throwaway pod using kubectl run test, rm, it, image equals busybox, wget. Namespaces give you logical isolation within a single cluster. Think of them as folders. Different teams, environments, or applications can each live in their own namespace with separate RBAC policies, network policies, and resource quotas. Look at the diagram. The same cluster contains a dev namespace and a prod namespace, each with their own pods. A pod named API in dev and a pod named API in prod can coexist without any naming conflict. Beat Kubernetes ships with 4 built-in namespaces. Default is where your resources land if you don't specify one. Kubesystem holds all the control plane components. Kube-public is readable by all users. It holds cluster info. Kubenode lease is used internally for node heartbeats. Click here are the namespace commands you need to know. Kubecan create namespace dev. Use namedave on any Kubecan command to target that namespace. Kubecan col get pods, A to see all namespaces at once. And critically, kubeconfig set context, current namespace equals dev, sets your default namespace in the current context, so you don't have to type ndev on every command. Beat, for cross-namespace service access, use the full DNS name, service.namespace.svc.cluster.local. That pattern appears in real configs constantly. Applications need configuration, database hosts, log levels, feature flags. And they need credentials, passwords, tokens, certificates. Kubernetes handles these with 2 resources: config maps for non-sensitive data, and secrets for sensitive data. Config maps store key value pairs, or entire config files. The YAML on the left shows a config map with two simple values and a multi-line config.ini file. You can consume it two ways. Inject all keys as environment variables using env from, or mount the entire config map as a directory of files using volumes and volume mounts. Click secrets work the same way, but values are base64 encoded. Note that base64 is not encryption, it is just encoding. The most important creation method for the exam is the imperative kubectl create secret generic with Brent from literal. You can decode a stored secret value with kubectl get secret, combined with -ojson path and piped into base64d. Beat know both consumption patterns cold, env from/env value from.secret key ref for environment variables, and volumes.secret with volume mounts for file-based secrets. Both appear in exam questions. Storage in Kubernetes follows a three-layer model. Let's walk through it with the diagram. At the top, you have the storage class. This is the blueprint that tells Kubernetes how to provision storage dynamically. It references a provisioner, like the AWS provisioner, and sets parameters like volume type. Next, you have the persistent volume, or PV. This is the actual piece of storage. It could be a network disk, an NFS share, a cloud volume. The PV is a cluster-level resource, not namespace scoped. Then you have the persistent volume claim, or PVC. This is the user's request for storage. It says I need 2 GB with read-write-once access. Kubernetes finds a matching PV and binds them together. The PVC is namespace scoped. Finally, the pod mounts the PVC as a volume. Click. The YAML walkthrough on the right shows. First, define the PV with capacity and a host path. Then create the PVC requesting storage. Then the pod mounts the PVC, using persistent volume claim.claim name. Click. The 3 access modes are critical. Read-write-once. One node can read and write. Read-only many nodes can read. Read-write many nodes can read and write. Not all storage backends support all 3 modes. Know that limitation. Let's talk about 2 advanced networking features, network policies and ingress. By default in Kubernetes, every pod can talk to every other pod in the cluster. That is a security risk. Network policies let you define firewall rules at the pod level using label selectors. Look at the YAML on the left. This policy selects pods with the label role DB and restricts their inbound, ingress, traffic to only come from pods labeled role, web on port 5432. Any traffic from other pods is dropped. The important warning here, a network policy only affects the pods it selects. Pods that are not selected by any policy remain fully open. Start denying with a default deny policy if you want to control everything. Click Ingress is an HTTP routing layer. Without Ingress, you'd need a separate load balancer service for every application. With Ingress, a single Nginx controller acts as a reverse proxy and routes requests to different services based on the URL path or hostname. The diagram shows exactly this. Traffic to/API goes to the API service. Traffic to/ goes to the app service. The YAML defines these rules under spec.rules. The ingress class name field tells Kubernetes which ingress controller to use. Beat for the exam. Know how to create a basic ingress with path-based routing. That is a common task. Next. Security access in Kubernetes is controlled through role-based access control RBAC. The model has 4 objects: roles, cluster roles, role bindings, and cluster role bindings. Look at the diagram. A subject, which can be a user, a group, or a service account, is connected to a role via a role binding. The role defines what API operations are allowed, called verbs like get, list, create, delete, and on which resources, like pods, services, deployments. Beat. The key distinction. A role is namespaced. It only applies within a single namespace. A cluster role applies cluster-wide and can grant access to cluster-level resources like nodes. Click the YAML on the left shows a role named podReader in the dev namespace. It grants get, list, and watch on pods and pod logs. Then the role binding connects that role to the user Alice. The imperative commands on the right are what you will actually use in the exam. There is no time to write YAML for RBAC. Kubectl create role and kubectl create role binding are your friends. Click in this command kubectl auth can I list pods as equals Alice nandev. This is how you verify that your RBAC setup is working correctly. The exam will ask you to set permissions and then verify them. Use this command. Beat service accounts are identities for pods. When a pod needs to call the Kubernetes API, say an operator or a CI pipeline, it uses a service account token. Know how to create one and bind a role to it. Next. The scheduler picks nodes for pods automatically, but you can influence or force its decisions using 3 mechanisms: taints, tolerations, and node affinity. Taints are applied to nodes. They say don't schedule pods here unless the pod explicitly tolerates this taint. For example, you might taint a node with GPU equals true, no schedule to reserve it exclusively for GPU workloads. Tolerations are applied to pods. A pod with the matching toleration can land on a tainted node, but it's not forced to. Look at the 3 taint effects in the table. No schedule prevents new pods from landing. Prefer no schedule is a soft version. The scheduler tries to avoid it, but won't guarantee it. No execute is the strongest. It evicts pods that are already running on the node and blocks new ones. This is what happens automatically when a node goes not ready. Click Node Affinity goes further. The YAML shows 2 flavors. Required during scheduling, ignored during execution is a hard rule. The pod will only schedule on nodes with disk type equals SSD. Preferred during scheduling, ignored during execution is a soft preference. The scheduler prefers nodes and US East 1, but will place the pod elsewhere if necessary. Click for simple use cases. Node selector is the quickest approach. Just add a label key value pair to the pod spec. And node name bypasses the scheduler entirely. Use it in the exam when you need to place a pod on a specific node without writing affinity rules. Next, every production cluster needs maintenance. OS patching, hardware replacement, Kubernetes version upgrades. Here is the proper procedure. When you need to take a node offline, you follow 3 steps. First, cordon the node with kubectl cordon node 1. This marks the node as scheduling disabled, so no new pods will be placed on it. Existing pods keep running. Second, drain the node with kubectl drain node 1. Ignore daemon sets. Delete empty dir data. This evicts all running pods, which deployments will reschedule on other nodes. The ignore daemon sets flag is needed because daemon set pods are expected to run on every node and can't be rescheduled elsewhere. The delete empty dir data flag handles pods using empty dir volumes. Then perform your maintenance. Then third, uncordon the node to bring it back into rotation. Click for a Kubernetes version upgrade using kubdata-m. The process has 6 steps. First, upgrade kubdem on the control plane. Second, run kubdem upgrade plan, and then kubdem upgrade apply to upgrade the control plane components. Third, upgrade kubelet and kubectl on the control plane node and restart them. Fourth, drain each worker node in turn. Fifth, on each worker node, upgrade kubdem and run kubdem upgrade node, then upgrade kubelet. Sixth, uncordon each worker. This is a heavily tested procedure. Practice the full upgrade sequence in your lab environment before the exam. Next, this is one of the most important topics in the entire exam, and it always appears. You must know how to back up and restore etcd. Why? Because etcd holds the entire state of your cluster. If etcd is corrupted or lost, your cluster state is gone. Backups are your disaster recovery plan. To back up, you use etcdctl with etcdctl _ API equals 3. The command is etcdctl snapshot save, followed by the output path. The critical detail, and where most people fail, is that you must provide 3 TLS certificate flags, kcert, cert, and key. You'll find the exact paths by looking at the etcd pod manifest at /etc /kubernetes /manifests /etcd.yaml. After saving, always verify with etcdctl snapshot status. Click to restore. You'll use etcdctl snapshot restore with a new data-dir path. This creates a fresh etcd data directory from the snapshot. Then you need to update the etcd static pod manifest to point at the new data directory. Change both the data-dir flag and the host path volume. The kubelet will detect the changed manifest and automatically restart the etcd pod. Click the diagram summarizes it. Running cluster, right pointing arrow snapshot, save right pointing arrow snapshot, restore, right pointing arrow, update manifest, equals restored cluster. Click the callout node is critical. Always provide all 3 TLS flags. If you run etcdctl without them against the TLS-enabled etcd, you will get a connection refused error and waste exam time. Copy the certificate paths directly from the etcd pod manifest. Next, beyond deployments, Kubernetes has 3 more workload types you need to know. Click daemon sets. A daemon set ensures that exactly 1 pod runs on every node in the cluster. When a new node joins the cluster, the daemon set automatically deploys a pod to it. When a node is removed, the pod is garbage collected. Use cases include log collectors like FluentD, monitoring agents like Node Exporter, and CNI plugins like Calico that need to configure networking on every node. Click stateful sets. These are for stateful applications like databases. The key difference from deployments. Pods get stable, predictable names. POSTGRES0, Postgres1, POSTGRES2. They are created in order and deleted in reverse order. Each pod gets its own persistent volume claim that survives pod restarts. This guarantees that POSTGRES0 always gets the same storage volume, which is critical for database replication and leader election. Click Jobs run a task to completion. Unlike deployments, which keep pods running forever, a job creates one or more pods, waits for them to exit successfully, and then stops. Use cases include database migrations, batch processing, one-time maintenance scripts. A cron job wraps a job with a schedule using standard cron syntax. The example runs a backup job every day at 2 a.m. The cron job creates a new job at each scheduled time, which in turn creates the pod. Every container in a pod should declare its resource requests and limits. This is fundamental to cluster stability. Requests are what the scheduler uses to find a suitable node. If a pod requests 250 millicores of CPU and 256 megabytes of RAM, the scheduler only places it on a node that has that much available. Limits are the hard cap. If a container tries to use more CPU than its limit, it gets throttled. If it exceeds its memory limit, the kernel kills it. You'll see OOM killed in the pod status. Beat 1 millicores, 1000 meters, equals 1 CPU core. So 250 meters is a quarter of a core. Click now look at the QoS classes diagram. Kubernetes assigns every pod a quality of service class. Guaranteed pods have requests equal to limits for all containers. These are the last to be evicted during resource pressure. Burstable pods have requests set, but less than limits. Best effort pods have no requests or limits at all. They use whatever is available, and they are the first to be evicted when the node runs out of memory. Never run production workloads as best effort. Click Limit Range lets you set default requests and limits for containers in a namespace. This way, any pod deployed without explicit resource specs automatically gets sensible defaults. Resource quota puts a hard ceiling on total resource consumption across the entire namespace. It prevents a single team from monopolizing cluster resources. Kubernetes needs to know whether your application is healthy. It uses 3 types of probes to find out. Look at the flow diagram. When a pod starts, the startup probe runs first. It gives slow-starting applications time to initialize without being killed. Once the startup probe passes, the liveness probe takes over and runs periodically for the rest of the pod's life. In parallel, the readiness probe also runs continuously. The actions on failure are different for each. If the liveness probe fails, Kubernetes restarts the container. Use this to recover from deadlocks or corrupted internal state. If the readiness probe fails, Kubernetes removes the pod from the service endpoints. It stops sending traffic to it, but does not restart it. Use this for temporary unavailability, like when the app is still warming up its cache. The startup probe protects slow-starting apps from premature liveness restarts. Click the YAML shows all 3 probes configured with HTTP GET checks. Key fields: initial delay seconds. How long to wait before the first probe? Period seconds. How often to probe? Failure threshold. How many consecutive failures before action is taken? Click and at the bottom, the 3 probe methods. HTTP GET makes an HTTP request and expects a 2xx response. TCP socket checks if a port is open. Exec runs a command inside the container and checks the exit code. Ext. We are now in the 30% domain troubleshooting. Master this and you pass the exam. Look at the decision tree. You start with kubectl get pods. If a pod shows pending, run kubectl describe pod and look at the events section at the bottom. The events will tell you exactly why it can't be scheduled. No nodes fit due to resource pressure, a taint mismatch, a PVC that can't be bound. If the status is crash loop back off, the container is starting and crashing repeatedly. Run kubectl logs pod to see what the application is printing to std out. If the container crashed before you could grab logs, use kubectl logs pod previous to see the logs from the previous crashed instance. Image pull back off means the container runtime can't pull the image. Check the image name and tag for typos, and check whether the pod needs an image pull secret to authenticate with a private registry. OOM killed means the container exceeded its memory limit and was killed by the kernel. The fix is to increase the memory limit. Click for a node not ready scenario, SSH, onto the node and check system CTL status kubelet. Then check the systemd journal with journal CTL-U kubelet. Look for errors about the container runtime, disk pressure, or networking. Click and here are the utility commands that make troubleshooting fast. Kubectl get events. Sort by equals last timestamp gives you a chronological view of what happened. Kubectl debug lets you attach an ephemeral container to a running pod to inspect it without modifying the pod spec. Kubectl CP to pull log files out of pods, and kubectl port forward to test a service locally without an ingress. The second major troubleshooting scenario is broken service connectivity. You deploy an app, create a service but requests fail. Here is the systematic diagnostic approach. Step 1. Confirm the service exists and has endpoints. Kubectl get endpoints web SVC. If the endpoints column shows less than none greater than, you have a label mismatch. The service selector does not match any pod labels. This is the #1 cause of service connectivity failures. Step 2. Verify the labels. Kubectl get pods, show labels, and compare the output to the services selector fields shown in Kubectl describe, SVC web, SVC. Step 3. Test DNS resolution from inside the cluster. Spin up a temporary busybox pod with Kubectl run test, rm, it, image equals busybox, and run nslookup web, svc.default.svc.cluster.local. If DNS fails, your core DNS is broken. Step 4. Test HTTP connectivity from inside the cluster, using the same temporary pod with wget or curl. Step 5. Check that core DNS and kube proxy pods in kube system are running and healthy. A crashed core DNS pod means DNS-based service discovery is down for the entire cluster. Step 6. Check network policies. If a network policy is blocking traffic, it will silently drop packets with no error message to the client. Look at the core DNS diagram. Pods use short names like web SVC for same namespace lookups. For cross namespace, use web-svc.prod. The full FQDN is web-svc.prod.svc.cluster.local. All of these resolve via core DNS running in kube system. Next, the kubeconfig file at /.kube/config is how kubectl knows which cluster to talk to and as which user. It stores 3 types of objects: clusters, users, and contexts. A context ties together a cluster, a user, and optionally a default namespace. When you run kubectl get pods, it uses the current context to know which API server to connect to and which credentials to use. Look at the diagram. The kubeconfig holds a dev context pointing to the dev cluster as user Alice, and a prod context pointing to the prod cluster as user Bob. Switching between them is a single command, kubectl config use context prod. Click the essential commands, kubectl config view to inspect the file, kubectl get contexts to list all available contexts, kubectl current context to see which one is active, kubectl config set context, current, namespace equals dev to change the default namespace in the active context. Do this immediately at the start of a problem set to avoid accidentally running commands in the wrong namespace. Click the YAML on the right, shows the full structure of a kube config. Study it. The exam occasionally asks you to add a new cluster entry, set up a new user with a certificate, and create a context combining them. Let's talk strategy. 2 hours is not much time. Speed and fluency with kubectl is everything. Click first thing you do when the exam starts. Set these aliases. Alias k equals kubectl. You will type this hundreds of times. Alias kn equals kubectl -n. Then export do equals dry run equals client YAML, and export now equals grace period equals 0 force. These 2 exports are game changers. Let me show you why. Click instead of writing a pod YAML from scratch, you run kubectl run mypod image equals nginx $do greater than pod.yaml. That generates a complete, valid pod manifest in 1 second. Same for deployments. Kubectl create deploy mydep image equals nginx replicas equals $3 do greater than dep.yaml. Then you open the file, make whatever tweaks the question requires, and apply it. Massively faster than writing YAML from memory. Click quick time-saving one-liners. Kubectl get events sort by equals last timestamp for recent cluster events. Kubectl logs -lapp equals web all containers to stream logs from all pods of a deployment simultaneously. Kubectl get pods -o wide -field -selector spec .node name equals node 1 to see what's running on a specific node. And kubectl get pods sort by equals last status .container statuses 0.restart count to find the most crash looping pod immediately. Click know these file locations by heart. Static pod manifests are at /etc/kubernetes/manifests. This is where the control plane pods live. Certificates are at /etc/kubernetes/pki/. The etcd data directory defaults to /var/lib etcd/. CNI configuration is at /etc//cni/net.d/. Next, let's zoom out and look at the full exam picture one more time. Troubleshooting at 30% is the heaviest domain. You need to be fluent at diagnosing broken pods, nodes, services, and network connectivity from the command line. Practice breaking things in your lab and fixing them. Cluster architecture at 25% covers the components we discussed, and critically, the etcd backup and restore procedure, plus the KU-BDEM cluster upgrade workflow. Both of these will appear. Services and networking at 20% means services, ingress with path-based routing, network policies restricting pod-to-pod traffic, and DNS troubleshooting. Workloads and scheduling at 15%, deployments with rolling updates and rollbacks, daemon sets, scheduling with node affinity and taints, resource requests and limits. Storage at 10%, create a PV, a PVC, and mount it in a pod. Know the 3 access modes. Click, and here is your practice checklist. Work through every single item on this list in a lab environment. Use KubeNet to set up a 3-node cluster on VMs, or use tools like Kind or K3s. The exam is purely hands-on. Reading about these topics helps you understand them. Doing them repeatedly is what passes the exam. Duration: approximately 40 seconds. This slide is your Kubectl quick reference. Bookmark it. Put it up on a second monitor while you study. The commands are grouped by category. Get and describe, your diagnostic workhorse. Create and apply, manage manifests. Imperative shortcuts, fast resource creation without writing YAML. Rollouts, managing deployments. Debugging, logs, exec, top, port forward. RBAC, role creation and permission checks. Node management, cordon, drain, uncordon, label, taint. Know all of these. Run them against a real cluster until your fingers type them automatically. Speed is the difference between finishing and not finishing. Let's close with the 10 things you absolutely must remember. Click 1. Kubernetes architecture. Control plane, API server, etcd, scheduler, controller manager. Worker nodes, kubelet, kube proxy, container runtime. 2. etcd is the source of truth. Back it up regularly. Know the exact etcd-ctl snapshot save command with all 3 TLS flags. 3. Use deployments for stateless apps, stateful sets for stateful, daemon sets for per-node agents. Never create raw pods in production. 4. Services use label selectors. A label mismatch between the service selector and pod labels is the #1 connectivity bug. 5. RBAC, role plus role binding for namespaced access, cluster role plus cluster role binding for cluster-wide. Use Kubectl auth CANI to verify. 6. Storage chain, PV at the cluster level, PVC at the namespace level, mounted in the pod. No, read-write once, read-only many, read-write many. 7. Taints repel pods. Tolerations allow pods through. Node affinity attracts sods to specific nodes. 8. Troubleshooting workflow. Kubectl get to spot the problem, describe for events, logs for application output, exec to get inside, events for cluster-wide timeline. 9. Set your exam aliases immediately. Alias k equals Kubectl and export, do equals, dry run equals client, OYAML. Use imperative commands with dry run to generate YAML at speed. 10. Troubleshooting is 30% of the exam. Drill it the most. Ext. That's a wrap. You now have a complete mental map of everything the CKA covers. The path forward is clear. Learn, practice, certify. Build the lab cluster, run through the practice checklist, and get comfortable with the time pressure of the exam format. If this helped you, drop a like and subscribe. Good luck on the exam. You've got this.